suppose first off, if you're wanting to do the any computational work or light-end work, one of the nice applications that you can have is GeoGebra. You can download it. It used to be a Java application. They're switching it to HTML5 based, so everything can code in that. Geometry and algebra. It was a research project, started off in Florida. I forget which Florida university. It's exploded since then. You know, in open source, not only do you have the ability to do computer algebra systems, algebra spreadsheets, probability, you know, things like that. It's kind of a kitchen sink, anything that would be from arithmetic on up through Calc 2, Calc 3, in terms of 3D mathematics. And so one of the nice things, like on the computer algebra system, one of the things you want to kind of a little bit, it remembers what you do. You can sign in, you can save certain things. But if you wanted to do 2 to the power, sorry, it was always 3. 3 to the power of 2003, comma 99. So all that sort of stuff that we've done before, say 3 to the power of 102. It'll do exact solutions in terms of the computer algebra system. That includes things like integration. Say x times sine of x squared plus c comma x. Oops. There's an integration. If I type it here, it'll autocomplete for me. And integral, sorry. Integral x times, all right, fine, use their field fun, x times the sine of x squared. Oh, great. Let's see if I can do it. Integral x times the sine of x squared plus c with respect to x. You have to get the function calls right. And I did that wrong, didn't I? Integral built-in functions. Actually calls it right this time. Should be able to do, I know it does integration by parts if I'm typing things correctly, but exact solutions, the modular work that we do, looks like I typed it wrong. Anyways, if you, in the web browser, it does a little bit better than the tablet, because the tablet's always trying to fight in back in between. It's like, hey, look, we have this nice little tablet. I'm like, just do the autocomplete and let me use an actual keyboard. But it assumes that you don't have that on a tablet, so it doesn't always work that way. So if you want to mess around with that, it does, like I said, 3D mathematics, integration, differentiation. Kind of the more fun part is if you would go to new, don't save it. If you go to a spreadsheet, one of the neater things about spreadsheets on this thing is, yes, you can do all the classic stuff of putting in numbers and calling, like, for example, B3, but the other thing that you can put in here is actually, you know, create functions, say, x to the third power, you know, do an x cubed, and then you can do things like integral of C3, and it'll take derivatives and plot that thing all out for you. So you can, not only is it a spreadsheet, it's actually a spreadsheet that allows you to put in all your symbolic mathematics. So like that one for the textbook asking for the extended Euclidean algorithm in the homework and things like that. This is kind of ideal because you can just not only do that, it'll also do infinite precision, so you can always check your answer and other components of it. And you can put in functions. This is also good for when you take your Calc 2 and you start doing like Maclaurin series. And it's like, oh, here's a function. Well, I need its derivative, its derivative, its derivative. Well, you can just simply say derivative of C1, derivative of C2, and you can evaluate things like, what is D3 evaluated at 1? And it would spit that back out because that's an actual function. So not only is it symbolic in location, you can actually do some pretty fun things with it. And you don't have to watch it, but you can actually watch the things. So for like the Maclaurin and the Taylor series approximations, this is kind of an ideal thing to teach it, to show students. Because you don't have to do things that take derivatives, it does it for you and things work out nicely. But that's just something to play with if you want. Other ones are, obviously Maxima allows infinite precision. Octave is a numeric acronym like MATLAB. So you can code MATLAB, you can code Octave. They're the same idea. So those would be available for you to kind of play around with. All right. Outside of that, questions? So as far as number theory goes, you're going to have to understand proofs by divisibility, prove the infinite number of primes, be able to understand how to do a lot of the prime and integer work, showing things that are congruent, using congruencies, as well as applications under cryptography. So for the next exam, it combines two concepts, and the exam will combine the number theory stuff that we've done, along with what we're talking about now, which is going to be induction. Now, induction, when you do 5.1 and 5.2, we're going to do 3 days on this. And they have two types of induction. They talk about weak and strong. A lot of textbooks that we do induction, they just have induction. Weak induction is a form of strong induction. It's just two different sorts of tautologies, and you can tell once we write these things down what we're trying to work with. Now, the purpose of induction is this is a new proof technique. And the idea of this proof technique is covering the following feature. If I want to, say, be given a propositional function say P of n, really doesn't matter. We put n's in there, but it's really just simply P of anything, right? P of anything. So I have some sort of propositional function that's declaring something about this thing I'm talking about, right? And so what are propositional functions? So for example, P of, say, a square chessboard, or might say checkerboard. And what I'm going to talk about square checkerboards, and what does this denote? This denotes that for a board that is 2 to the n by 2 to the n, well, what is 2 to the n where n is equal to 1, 2, etc. So what we're talking about is things like 2 by 2, 4 by 4, 8 by 8, 16 by 16, right? A power of 2 board. It's either 2 by 2, 4 by 4, 8 by 8, 16 by 16. With one missing piece. Something like this. I have a board that's one part's been pulled out of it. And that would be a 2 by 2 with one more missing piece. Can be tiled by L-shaped pieces. Seems awkward, but this is a propositional function. It simply says things like, okay, it doesn't matter if it's 2 by 2, 4 by 4, 8 by 8. Pull one part out. I'm always going to be able to tile it with these little L shapes. I'll completely cover it, no matter what. And so that's a propositional function, right? This is either true or false, right? And so one way we could actually prove this, if I assume when we go to things like, please prove this propositional function. When you mean prove a propositional function, proving a propositional function shows that for all elements of the set that's in its universe of discourse, this thing evaluates the truth, right? If one of those did not work, that would be the counterexample to this propositional function being always true. And so we have from that, the second thing is we have that P of this has a universe of discourse that is countable. And really what we're going to talk about, classic countability, this actually is the idea of what's called a well-ordering. But what I mean by that is the universe of discourse can be written as a set as a first element, a second element, etc. Right? It has a first element, a second element, a third element, a fourth element, for on. I've counted it out. Yes?
So it wouldn't work on a universal domain with like the reals that you could...
No. It has to be countable. Right? We have to have a first, second, third, fourth, fifth element. So there has to be some sort of bijection between the counting numbers and these objects, which really just simply says you have a first element, second element, third element. And our goal of a particular problem like this is to please prove for all n P of n. For all elements in the universe of discourse, this propositional function evaluates to be true. So if my example here of this whole square checkerboard thing, right, if I would take this universe of discourse question, I could say, well, example, the universe of discourse of this checkerboard would be a what? That's a 2 by 2, and then the next one would be bigger, which is 4 by 4, ... right? It goes 2 by 2, 4 by 4, 8 by 8, 16 by 16, and some one piece is missing in this, somewhere. So how many first element boards are there? How many pieces could be missing? 4, right? So there's going to be 4 of them. All right, how many second element boards? So how many 4 by 4s with one piece missing could there be? 16. By symmetry, you could rotate and things like that, but I just simply go through and just take out one of those. Like I could go through here and how about remove that one and tile it, right? There'd be 16 of those. Where it could be there or there. I'm just going to draw a 4 by 4, right? But there's one piece missing out of these boards. So that's an ordered universe of discourse. Got a first, second, third, fourth, all the way up to however we want. And now I want to prove this. All right. What are your techniques of proving for universal statements? The only ones we've done so far are, what if your universe of discourse is finite? If your universe of discourse is finite, you would do a proof by cases, right? Just handle all of them. Is my universe of discourse finite? No. Since universe of discourse is not finite, I cannot use proof by cases. I just can't go through this and do one at a time. It's just not going to work out. And so We can't use cases because it's not finite. And the second thing that happens a lot of time is we can't use generality for a lot of problems. What do I mean by generality? Generality would be something like this. Say, for example, solve ax squared plus bx plus c equals 0, right? The idea of generality is don't put any numbers down and solve all of them at the same time. Well, this checkerboard issue of a 2x2, 4x4, 8x8, there's no form of generality I can do on this. It's like, what would be the generic checkerboard representation that would represent them all? I don't got such a, it has to be 2x2, 4x4, it has to be those specifics, right? I can't just simply say this thing represents. Whereas this one, like on this problem, ax squared plus bx plus c equals 0, that represents what? All quadratics. And so you could solve it, and you would get things like x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a, right? I have solved all of them by just simply not putting down any numbers. I just put down these are a, b, and c are real numbers, and I'm going to come up with two solutions that will be like this by using a particular technique that solves them all. But if I can't use generality, I'm stuck. You have to deal with each one, but there's an infinite number of them, and I can't represent all of them with just some sort of, oh, let's not talk about numbers, let's just do them all. I can't prove by example. So what do? We have two tautologies that are useful. The first one looks like this. This will look a little bit different in the book. The book always uses 1 and n and things like that. We can do that. I usually like to talk about first elements rather than 1 because a lot of people get confused. When I write p of 1, it doesn't mean 1. P of 1, when you look at the book, means this is p of the first element in my universe of discourse. That's what the 1 represents. Because the universe of discourse is just these ordered list of objects, right? And so the first tautology that we have is p of the first element, and I have a for all k that p of the kth element implies p of the k plus first element So I have two objects here. I have this object in conjunction with this object. Those two objects together implying for all n p of n. What does for all n p of n mean? That simply says that the propositional function is true for all elements in the universe of discourse. This entire thing is a tautology. This is only a tautology from something that we'll have from Discrete 2. Right? I'll just tell you it's a tautology. We can show it's a tautology, but we got to wait. The tautology nature of this comes from the countability of the universe of discourse. And it's a particular type. This is called a well-ordered object, which means that not only if we take any subset, there is a first element that's smaller than all the others, which is the idea. We need to have a first for this to occur. Not all things, not all objects have that feature. So for example, if I take the negative integers, right, from negative infinity to 1, is there a least object? No, there is no least object that starts on the left-hand side, right? So we have to have a least object to allow this to be a tautology. All right, so what do I have? I have a larger implication, right? I have this implication. This entire left side implies the right side, and this entire big implication is a known tautology. Well, if I have a large implication, right, if we know that left implies right is simply always true, what does that tell us? That tells you that, well, the left and the right, left could be true or it could be false. The right side could be true or it could be false. Under normal behavior, this is either true or it's false, right? By saying that left implies right is always true, what am I saying about that second line? I'm telling you left implies right is just a tautology. What does that tell you about line 2? It doesn't exist. That never happens. Is everybody okay with that? Since we know that, that means it gives this feature. All right, let's take a second here. I know my implication is a tautology. That means that this entire second row is gone. All right. What am I asking people to show? I'm asking people to show what? That for all n, this is what I care about. I care about the for all n p of n needs to be true. Look at each of these rows. When can for all n p of n be true? Well, if it was true, it's possible that the left-hand side was false, right? But then I don't know anything. If the left-hand side is false, I don't know if the right is true or false, right? It could be either. But on the other hand, if the left-hand side is true, what's the only possibility for the right-hand side? It must be true. So what that tells us is, oh, wait, you want the right-hand side to be true? Well, that would be a very nice byproduct to simply show the left. Just show the left is true. If I show the left is true, the right must be true. So if we want the right to be true, show left is true. So that's what I've reduced my problem to. I want the right. I can't do it. It's too hard. Well, by this tautology, I will have done that if I can show the left is true. But what does it mean for the left-hand side to be true? The left looks like this. P of the first and that's one thing. And the second thing is for all k, P of the kth needs to imply P of the k plus first. Notice I'm changing it up a little bit. I'm using, kth and first. Why am I saying it that way? Is I want you to understand that these are the element order. This is not the number 1. This is not the number k. It's the first object. It's the kth object. It's the k plus first object out of the universe of discourse. That's my left. It's conjunction. What's the only way that this could possibly, if I have two objects under conjunction and it needs to be true, what do I need to do? Show they're both true. So what has to have is show this is true becomes two things. I have to, 1, show P of the first element is true, and 2, show for all k, well, we understand that for all elements it's enough. Rather just simply usually just show P of the kth element implies P of the k plus first. element is this is true. So showing a for all n p of n has been reduced to two cases. Show the first object. Well, if I need to show the first object is actually forms a tautology, that's existential, right? Just plug in the first element and show that that evaluates to be true. So what's the first element? Check. Is it true? It's true. The propositional function holds for the first element. Good. That's the first case. The second case is now, well, that's an implication. All right, what techniques do we have for implication? And here, this is a generalization. We plug in, I know I have a kth element. Well, what does the kth element look like? For example, on this chessboard, what would that be? That would be a 2 to the k by 2 to the k board. It's literally a 2 to the k by 2 to the k board. We have that as my left. Well, what's k plus 1? 2 to the k plus 1 by 2 to the k plus 1 board. That would be what the next board would look like. So we have generalization. I just simply plug a k in, we're good. I can generalize that. But how do I show implication? Direct. And what's our non-direct proofs? Contraposition and contradiction. So all of the proof techniques that we've already learned can be applied. I just have two things to show. One's existential, prove it's true. The second one is show this implication. If it's direct, what would you do? Assume the left. Assume that you can tile a 2 to the k by 2 to the k board. Just assume that. And then show what? Because of that, I can tile a 2 to the k plus 1 by 2 to the k plus 1 board. So you would assume the left, show the right. What would be an indirect? Let's say contraposition. What would that look like? Assume you can't do the k plus first, then show that you can't have the k. What would be contradiction? Assume that you can do the k, but you cannot do the k plus first. And then show that that is actually false. So we still have the same things. These two things together are called induction. The first case is called basis. That's the basis case. And the second one is called the inductive case. Sometimes instead of case, we just use the word step. So induction itself, when I talk about this is called weak induction, and we'll say why here in a bit. A second tautology on this is that we have P of the first implies for all k, P of 1 and P of the first element and P of the second element and everything up to P of the kth element implies P of the k plus first element. All of that implies for all n P of n, and all of this is your tautology. What's the only difference between the two? That right there. Let's consider this a problem of lining up a grade school kids to go into a building. And so all the kids line up. So my universe of discourse is all of the kids in order. And assume there's an infinite number of them. So I've formed a universe of discourse. I've showed that all of the infinite number of grade school kids, are all countable. I have my first element. But the way I counted them was in increasing size. The smallest kid is number 1, the next bigger kid is number 2, the next bigger kid is number 3, etc. But they increase in a rather unusual size. What happens is, okay, I simply say that I can push over all the kids. That's my universe of discourse. I can push them all down. Like dominoes, because they're all stacked up, because I've set them up for dominoes. Okay, well, what would I do? Well, if I want to say that I can push over all of the kids, that's what I want to be true, it's been reduced to the basis case and the inductive case. If I can show the basis case and the inductive case, then this will be true. My inductive case looks a little bit differently. But on the end, this is still the previous induction, except I'm just simply keeping track. What happens is this. What's the basis case? Can I push over the first kid? So what do? You push him over. It's true. I can knock him down. Okay, then what do? The following thing has to be true. If the first kid and the second kid and the third kid, all the way up to the kth kid, have all fallen on top of each other, it's enough for all of those kids together to push over the k plus first kid. Now that may be necessary if this k plus first kid is so much larger that the kid in front of him is not big enough to push him over, right? But him and all the kids behind him together can do it. All right, the difference between this and the one before it looked like this. For all k, p of k implies p of k plus first. This one was like, you know what, I really didn't need kids 1 through k minus 1. The kth was strong enough to knock over the k plus first. I didn't even need to. Now, have they all fallen down? Yes. Are they all leaning on all the way up to the kth kid? Yes. Did I actually need their strength? For some problems, the answer is no. It's enough to just simply say the kid before can knock over the kid. But what if this is a problem that requires all of them leaning? I'm going to need them all. So really, these are the same induction, because the kth just simply says the weak, this first version, we call it weak induction. The weak induction really just simply ignores the fact that everybody up to k is helping k to work on k plus 1. This one pays attention to it. It says, no, I need them all. And so we call that strong induction. Is weak induction strong induction? Yes. It just simply says I don't need to really pay attention to everybody. So that's one of the reasons why most people just simply say the term induction and they don't make weak a special case. All right, strong induction is absolutely necessary for a problem that would require a lot of people before to get the next, or several people, or one special one in the middle to get the next. The only thing that changes between the two is no matter what for induction. So when I say induction, one, you have your basis, which means show that whatever you're talking about, first element, is true. Show the basis step. Show you can knock over the first kid. Show you can tile a 2x2 board. The second one has two forms, what we call weak induction. For weak induction, we want to show that P of k implies P of k plus first. I don't need everybody before, I just need one before. It's enough. Or, rather move up to strong induction. And strong induction is to show that P of 1 and, P of the first element and P of the second element and everything up to P of the kth element working together can show the P of k plus first element. Now, you may not need everybody in that group. You might need just a couple of them. You might need one of them out of the middle. You might need just the case, which would mean that's actually weak induction, right? It just simply means that we need some of those. But we assume that they're all true, right? Because this is implication. If it's implication, it's good enough to simply say, let's assume it out, right? Actually, here's a question for you. Just for a little bit. Anybody remember this logical equivalency? If I had A and B implies C, this has to be A implies C, B implies C. But what's the operator in the middle? That and becomes an or, which means that, see that and going across, it's enough to do one. What's weak induction? The case. What's strong induction? Maybe one or more of these are actually are true, but it's still just going to be true, right? That'll still be true. Because it's or. If one of them's true, the entire thing is true. So if you only need one of them, that's all you needed. If you need all of them, it's still true. You just go through it and you use them all. Is everybody okay with that? That's why weak induction really is strong induction. It's just focus on the end rather than the beginning. Some problems, that's enough. Some problems, this is absolutely necessary.
Is there a way to pick up on which one we should use?
If it's in the weak induction section, it's going to be weak. If it's brought from the strong induction section, it's strong. What about us? You don't, right? You just go through it and you try to work it out and try to say, oh, do I need? You kind of just dig it out and try to figure it out the hard way. Now, on the other hand, since they're essentially equivalent, that would tell us that all strong inductions reworded in a special way can become a weak induction, or a weak induction is strong induction, right? It doesn't matter. And so a lot of times if you just simply restate your propositional function in a better way, it's weak induction. But they'll do the same proofs, so you can just simply twist them around a little bit. All right, let's try the simplest example, which is the one I had you guys hand in. Okay, so example. Let's say that my statement P of n an integer, say what, not an integer, but a positive integer, denotes the following. 1 plus 2 plus everything up to n does indeed equal n times n plus 1 over 2. If I put this in English, the nth triangular number is the number n times the number n plus 1 all divided by 2. Because the left-hand side is just a triangular number. That'd be putting it in English. In this sort of symbology is that equal is true. Now we know that. That's why we do it, right? Okay, what's your universe of discourse? Writing down the universe of discourse can help you solve this problem. All right, n's a positive integer, right? So what's my first? N is 1. What's my next? N is 2. N is 3, right? Etc. Normally we would just write what? 1, 2, 3, right? That's normally what we would do. But what they mean is n is equal to 1, n is equal to 2. So obviously, what is my first element? So I'm going to prove this by induction. So then what's the first thing I have to handle? The basis. But what's the basis? P of the first element, which happens to be what? P of n equal to 1. Please write it this way. Because when we really tweak this up to make it odd objects, things like we are going to have a snowball fight with an odd number of people. What's your first element? And I want to have, well, let's say we start off at 3 or more people. So the first group, I would have 3 people here. What would be your second element? There's 5 people here. What's your third element? There's 7 people here. And my statement is, everybody is standing a unique distance apart, right? And the rule is you must throw a snowball at the person closest to you. And the propositional function is, no matter what, there's always one person who is not hit by a snowball. And so, how would I have to show that? Well, what could you do? Can you do this by cases? Have a snowball fight with 3 people. Have a snowball fight with 5 people. Have a snowball fight with 7 people. Would those cases ever end? No, so I can't prove by cases. So I have to move on to induction. Anyways, so my first element is P of n equals 1. What does that mean? If I plugged in n equals 1, what's supposed to happen?
1 equals 1 times 1 plus 1 over 2.
That would denote, so P of n equal 1 denotes what? What's the left-hand side of that equal side? 1. What's the right-hand side? 1 plus 1 plus 1 all over 2. Is that true? Yes, that's true. 1 equals 1. That's what I want to have happen. So a lot of the problems we deal with are algebra, right? Hey, look, this is equal. Yeah, that's a tautology. Okay, what about inductive? I'm going to use weak, which would be P of the kth needs to imply P of the k plus first. All right, note. What does the P of the kth look like?
1 plus 2 plus plus k plus 1 over 2.
What does P of k plus 1 look like?
1 plus 3 plus plus k plus k plus 1.
And what is that supposed to be equal to?
K plus 1 times k plus 1 plus 1.
I'll just make that plus 2. Right? So what are we doing? This equality needs to imply the bottom equality, right? The first equality, the left-hand side of this here, these left-hand sides, normally what do? We assume the left and show the right if we do this by implication. The left-hand sides of these implications, the P of k and the P of 1 to the P of k, are called the inductive hypothesis. Because what's the left-hand side of an implication? The hypothesis. What's the right-hand side? The conclusion. Why is it called the inductive hypothesis? Because it's in the inductive case, right? It's in the inductive step. So in the inductive step, the thing that I'm going to assume is normally called the inductive hypothesis. So everybody okay with when I use the word inductive hypothesis, I'm saying under the inductive step, the left must imply the right. I just assume the left under direct assumption, under a direct proof. So we just say these left sides are called the inductive hypothesis. Since that's the inductive hypothesis, so to prove this, we just simply assume that indeed 1 plus 2 plus everything up to k does indeed equal k times k plus 1 over 2. I assume this equality is true. Why? It's the left side of an implication. That's how you do direct proofs. You assume the left and show the right. What's my goal? That the k plus first step must be true, right? Must be true. I need to show that second equality. I assume this. We assume we show, there's two ways to do this assume show. How do you show things are equal? If you need to show an equality, there's two ways to do it. One, start with an equality and do things that you're allowed to do to an equality. Add like things to both sides, multiply except for 0, on both sides, right? Those are things that we're allowed to do. The second is to do expression work. Start with the left-hand side and replace things with their equal. Well, this is equal to this, replace it. Well, this is equal to this, replace it, right? So you have two approaches. Start with an equation and do equation work. Start with an expression and do an expression work. Those concepts do the same thing of any of these forms. So what do you want to do? Do you want to start off with this equality and do things until do correct in logical things until this equality looks like the second equality? Or do you want to start with the second equality, take the left-hand side, and start replacing things with their equal? You want to try that technique? Okay. So we assume this is our inductive hypothesis. That's the inductive hypothesis. So, what is 1 plus 2 plus 3 plus everything up to k plus 1? Well, this stuff here, I already have an equality for that, right? I'll replace it with its equal, which is, that's just simply k times k plus 1 over 2, and I still have my k plus 1. Is everybody okay with that? Right there, that's the inductive hypothesis. I replaced things with their equal. All right, look at where I want to go. I'm starting with this, and I want to get to there. What's the big difference between that, where I want to go, and where I'm currently at? How many fractions do I currently have? 2. How many fractions are up there? 1. So how do we put those fractions together? Like base and atom, right? So this is actually equal to k times k plus 1 plus 2 times k plus 1 all over 2. Or the bottom's the same? Yep. Now for my top, what do I notice? There's a factoring. Well, do I see common factors? That equals k plus 1. What's left over? K plus 2 over 2. Have I shown what I wanted to show? That indeed, 1, 2 up to the k plus 1, because the inductive hypothesis is true, is also k plus 1 times k plus 2 over 2. Is everybody okay with that? So because the first one is true, the second one is true. That's the whole point of it, showing an implication. So we're good. And so therefore, my inductive step has been shown to be true as well. All right. This process is completely up to you. Some students love taking equals and then just simply, oh, I notice that all I'm short is a k plus 1. So I'm going to put a k plus 1 on one left and a k plus 1 on the other. I'm allowed to do that. The equality is still the equality. And then the second equality shows up. Some people like equational work. Some people like expressional work. Which one do you pick? Whichever form of algebra, if it's an algebra problem, you're most comfortable with. But we don't always have algebra problems. If I go back to that tiling problem, that a 2 to the n by 2 to the n board with one piece missing can be tiled by this shape. Right, this little L-shaped piece can tile this thing out. Obviously, and what we're looking at is a 2 by 2 for the universe of discourse. What we're talking about is a 2 by 2, then a 4 by 4, then a 8 by 8, etc. Right? That's my universe of discourse. All right, what's my basis? It's a 2 by 2 with one piece missing. So what does your basis look like? It looks like this, or it looks like this, or it looks like this, or it looks like this. There are 4 objects in my basis. Can all of these be tiled by a L-shaped piece? Yes, and obviously all of them are tiled. Obviously each can be tiled by that. Is everybody okay with that? So this is obviously true. What about the inductive? Inductive is, I have a 2 to the k by 2 to the k board implies a 2 to the k plus 1 by 2 to the k plus 1 board. So the question here is, assume that, show that. And your heart of this problem is going to be this. What do you notice about the difference as I increase in sizes? What's the difference between a 4 by 4 and a 2 by 2? A 4 by 4 is 4 2 by 2s. What about an 8 by 8 versus a 4 by 4? It's 4 2 by 4s. So what is a 2 to the k plus 1 by 2 to the k plus 1? It's 4 of these 2 to the k's by 2 to the k's. And so that's what we're going to use. But we have one issue. This 2 to the k plus 1 by 2 to the k plus 1 is 4 of these 2 to the k's, 2 to the k's, but only one of those 2 to the k's is actually missing something. All the others are completely full, because there's only one piece missing out of that. And so out of those 4 pieces, only one is missing a piece. The others are completely full. So I have to figure out how to tile a full board, or 3 boards that are full. And that'll be the idea behind that proof. All right, the attendance is going to be, finish that. It's in the book. It's one of the book examples. So, all right, that's it.